In today's lesson, we're going to solve linear inequalities involving two variables. We'll start by looking at a quick word problem, and then we'll graph linear inequalities. So this word problem here says, for a fundraiser, the math club agrees to sell candy bars and candles. The club's profits will be 50 cents for each candy bar it sells and $2 for each candle it sells. The club needs to earn at least $1,000 in order to pay for an upcoming field trip. So for part A, we want to write a linear inequality that describes the combination of candy bars and candles that must be sold. X will represent the number of candy bars sold, and Y will represent the number of candles sold. We know that the club needs to earn at least $1,000 in order to pay for the upcoming field trip. So let's come up with an expression to represent the total earned. The club is going to earn or profit 50 cents for each candy bar, and since X represents the number of candy bars sold, the total earned from the candy bars will be 50 cents times the number of candy bars sold, X. And we know that each candle is $2, and we're representing the number of candles sold with Y. So the total earned from the candles will be $2 times the number of candles sold, Y. So this expression represents the total earned. The club needs to earn at least $1,000. So the total earned needs to be at least $1,000. The symbol we use to represent at least is greater than or equal to, and the total earned must be greater than or equal to, or in other words, at least $1,000. Okay, so we've written a linear inequality that represents this situation. To compute the total earned, we take 50 cents times each candy bar plus $2 times each candle, and this total earned needs to be at least $1,000. Part B asks, will selling 500 candy bars and 350 candles earn enough for the trip? X represents the number of candy bars sold, so we'll plug 500 in for X, and Y represents the number of candles sold, so we'll plug 350 in for Y. Okay, I plugged in 500 for X and 350 for Y into this inequality right here. And we want to find out, does selling 500 candy bars and 350 candles earn us enough to go on the field trip? In other words, will that give us an amount that's greater than or equal to $1,000? If we compute this, 0.50 times 500 will give us $250, and $2 times 350 will give us $700. And if we take 250 plus 700, that leaves us with 950. 950 is not greater than or equal to $1,000, so selling 500 candy bars and 350 candles does not earn enough for the field trip. Next, we're going to quickly review how to determine whether an ordered pair is a solution to a linear inequality. Let's suppose we're given this inequality, and we want to determine if this ordered pair is a solution to this inequality. To determine if this is a solution, we just went ahead and plugged in 5/3 for X and 4 for Y, and we want to see if we get a true statement here. Let's see, if we take -2 times 5/3, we can do this by hand or on our calculator. If we do it by hand, it might be helpful to write that as -2/1, and then we just multiply the numerators to get -10, and the denominators to get 3, and then -5 times 4 will give us 20. Then we can either subtract these by hand by getting a common denominator, or we can just punch this into our calculator. Either way, if you take -10/3 minus 20, that will give us -70/3. And now we have to decide if this is a true statement or not. You might find it helpful to convert this to a decimal by just taking -70 divided by 3 in your calculator, and that will give you -23.3 repeating. And now it's a little bit easier to see that this is, in fact, a true statement. -23.3 repeating is less than or equal to -10. And because when we plug this ordered pair into this inequality, we get a true statement, we would say that the ordered pair 5/3, 4 is a solution. Now let's quickly check to see if this ordered pair is a solution to this inequality by plugging in -3 for X and -6 for Y. And let's see, this will give us a +6 plus 30 is less than or equal to negative 10, which will leave us with 36 is less than or equal to negative 10. This is not true. 36 is not less than or equal to negative 10. So since when we plug this ordered pair into this linear inequality, we get a false statement, that means that this ordered pair, negative 3, negative 6, is not a solution to this linear inequality. Inequalities are expressions involving inequality symbols, like a less than or a greater than, or a less than or equal to, or a greater than or equal to symbol. We just found that this ordered pair is a solution to this linear inequality. But linear inequalities involving two variables, x and y, typically don't have just one solution. They have infinitely many solutions. So while this ordered pair is a solution to this linear inequality, it's not the only solution. So notice, an inequality like this has an infinite number of solutions. Here's some examples of other ordered pairs that are solutions to this inequality. You could plug in any of these ordered pairs into this inequality and you'd get a true statement, just like we did over here. There are infinitely many ordered pairs that you can plug in and get a true statement. So the question is, let's suppose somebody asked you to solve this linear inequality. If there are infinitely many solutions to an inequality, how can we represent the infinitely many solutions? Well, we typically represent the infinitely many solutions of a linear inequality like this using a graph. On the next page, we're going to look at this exact same linear inequality, and we're going to see how we can use a graph to represent the infinitely many solutions. Now, there are different ways we can graph linear inequalities involving two variables, like this one here. You've likely learned one or both methods in your math background, but the method that we're going to review today is called the test point method. The test point method may not be the most common method for graphing linear inequalities, but it's a very important method, and it's a method that you'll use later on if you move on in math and graph more complicated graphs. So it's an important method to learn. To graph a linear inequality using the test point method, the first step is we're going to replace the inequality symbol with an equal sign and graph the resulting equation. If the inequality in the original problem is a less than or a greater than symbol, we use a dotted line to graph the equation. If the inequality in the original problem is a less than or equal to or a greater than or equal to symbol, we use a solid line to graph the equation. So for step one, I'm going to copy down the original problem, but replace this inequality symbol with an equal sign. Now we want to go ahead and graph. We've learned two different ways to graph a linear inequality. We can either find and plot the x and y intercepts, or we can convert this to y equals mx plus b form and then graph from there. You can use either approach, but the approach that I'm going to use is to write this in y equals mx plus b form. So I've just copied down this equation here. To write it in y equals mx plus b form, we want to isolate y, so let's add 2x. That will leave us with negative 5y is equal to 2x minus 10, and then let's divide by negative 5. That will leave us with y is equal to negative 2/5 x plus 2. Now that we've written it in y equals mx plus b form, we can graph. And when we're graphing using y equals mx plus b form, first we need to identify the y-intercept. The y-intercept is 2, so we can go ahead and plot that along the y-axis at 2. Then we use the slope to count the next point. The slope is negative 2/5. If your slope is negative, when you're graphing, I recommend putting the negative in the numerator instead of writing it out front. It makes graphing a lot more straightforward. So with slope, the top number tells you to go up or down. Since it's a negative 2, we're going to go down 2. And the bottom number tells you to go right or left. Since it's a positive 5, we go to the right 5. When graphing, you only need 2 points, so we can go ahead and draw our line through those 2 points right now. But when I'm graphing by hand, I always like to plot a few more points just to help make the graph a little bit more accurate. So I'll go down 2 and to the right 5. Notice when I'm plotting points using the slope, I'm moving rightward. If you want to move to the left, you've got to plot the slope backwards. So if I want to move backwards to the left, instead of going down 2, I go up 2. Instead of going to the right 5, I go to the left 5. Now, if your original problem had an equal sign in it, then you always graph using a solid line. But if your original problem has an inequality symbol, you have to decide if you need to use a dotted line or a solid line. Let's see, we have a less than or equal to symbol here, and it looks like if the inequality is a less than or equal to symbol, we use a solid line. So I went ahead and connected these points using a solid line. Now, if this had been an equal sign in the original problem, we'd be done. But if your original problem has an inequality symbol, you're not done after graphing the line. You will also have to shade. So that is step 2 of our test point method. Step 2, to help us decide which side we shade, we need to select a test point. Now, for your test point, you can pick any point as long as that point does not lie on the line. But there's one point that is the easiest one to pick, and that point is 0, 0. You can always pick 0, 0 for your test point as long as that point doesn't lie on your line. If your line goes through the point 0, 0, then you can pick any other ordered pair you want, as long as that ordered pair doesn't lie on your line. But for all of our examples, our line will not go through the origin, so we will always be able to pick 0, 0 for our test point. Next, we're going to plug the test point 0, 0 into the original inequality. So I copy down the original inequality right here. Be very careful. A lot of people will plug their test point into the y equals mx plus b form, and that can lead to incorrect answers. We only use the y equals mx plus b form to help us graph. So we plugged in 0 for x and 0 for y. That leaves us with 0 minus 0, or 0, is less than or equal to negative 10. Now, we have to ask ourselves, is this a true statement or a false statement? 0 is less than or equal to negative 10. That's a false statement. So let's just think through this logically. We just picked 0, 0 for our test point. Now, we have to decide, are the ordered pairs below the line solutions? Then we should shade below the line. Or are the ordered pairs above the line solutions? Because then we should be shading above the line. Well, we just found that 0, 0 is not a solution. So since this is not a solution, the solutions must be above the line. So I went ahead and shaded above the line. So let's go back and fill out our instructions here. If plugging in the test point results in a true statement, shade the area containing the test point. And if plugging in the test point results in a false statement, shade the area that does not contain the test point. Since plugging in the test point resulted in a false statement, that means we're supposed to shade the area that does not contain the test point, which is exactly what we did here. We shaded the area that did not contain the test point. So what does this mean? This means that every single ordered pair in this shaded region is a solution to this inequality. You could pick any point you want here and plug it in to this inequality and you would get a true statement. A solid line indicates that points on the line are also solutions to this inequality. So you could also pick any point on the line and plug that point in for x and y, and you would get a true statement. One last point of emphasis here, please remember to plug your test point into the original inequality. If you plug it into the y equals mx plus b form, you will often get the incorrect answer. The reason being is, notice we replaced the inequality symbol with an equal sign. If we had maintained that inequality symbol throughout our calculations here, when we divided by a negative, we would have had to flip the inequality right here. Often students will plug the test point into the y equals mx plus b form, and they'll forget to have checked if the inequality should have flipped at some point. So to avoid all of that confusion, I recommend making sure to plug the test point into the original inequality, not the y equals mx plus b form. One last example. Let's again graph this linear inequality using the test point method. The first step of the test point method is to replace the inequality symbol with an equal sign. And then we want to go ahead and graph. And the approach that I'm going to show you for graphing is to write this in y equals mx plus b form. Now, to write this in y equals mx plus b form, we want to isolate y. And there are several different ways we can do that. You're welcome to use a different approach, but the approach that I'm going to show you is that LCD approach that we've been practicing. That LCD approach says that if you have an equation involving fractions, you can quickly get rid of the fractions by multiplying each term by the LCD. So what is the least common denominator in this case? Well, the denominators here are 2, 8, and the implied denominator here is a 1. So the least common denominator, or the smallest number that 2, 8, and 1 all multiply into, is 8. So I'm going to go ahead and multiply this term, and this term by 8 over 1. Okay, now we should be able to do some canceling and our fractions will disappear. Let's see. 8 divided by 2 gives us 4, so we're left with 4x over 1, or 4x. These 8's cancel, so we're just left with negative y over 1, or negative y. And 8 times 1 gives us 8. Now we've used the LCD to get rid of our fractions. Now we can isolate y. Let's subtract 4x. That will leave us with negative y is equal to negative 4x plus 8. And now to isolate y, we can divide by negative 1. And that will leave us with y is equal to 4x minus 8. Now to graph, we start by identifying the y-intercept, which is negative 8. So let's go ahead and plot negative 8 along the y-axis. Next, we use the slope to count our next point. The slope in this case is 4, but it's helpful to write the slope as a fraction, so I'm going to write the slope as 4 over 1. We can start at our given point, and then we'll count up 4, 1, 2, 3, 4, and to the right 1. Now when we're graphing, we only need 2 points. We can go ahead and draw our line through those 2 points. But when I'm graphing by hand, I always like to plot a few more points just to help make the graph a little bit more accurate. So I'm going to continue moving up 4 and to the right 1. Now, if the original problem had an equal sign in it, we know we always just connect the dots with a solid line. But if the original problem has an inequality symbol, we always have to pause and ask ourselves, do we connect the points with a dotted line or a solid line? Let's see, we have a less than symbol here. So let's look back at our notes. We said if the inequality is a less than symbol, use a dotted line. So let's connect these points using a dotted line. Now, remember, when you're graphing problems involving inequalities, you also have to shade. So step 2 is going to help us decide, do we shade on this side of the line or on this side of the line? For step 2, we pick a test point. The test point can be absolutely any point that doesn't lie on the line, but the easiest point to pick is 0, 0. And you can pick 0, 0 as long as that point does not lie on your line. Now remember, we plugged the test point into the original inequality, which I've copied down here, and I plugged in 0 for x and 0 for y, and let's see if we get a true or false statement. 0 divided by anything is 0, so this is 0 minus 0, which gives us 0 is less than 1. 0 is less than 1 is a true statement. So let's look back at our notes. If plugging in the test point results in a true statement, we want to shade the area containing the test point. And logically, that makes sense. Our test point is right here. And when we plugged in our test point, we got a true statement, which means that this is a solution. And where we shade represents all of the solutions. So if this is a solution, it makes sense that we want to shade the area containing that point to represent the solutions. Now, I want to emphasize one more time, make sure you plug your test point into the original inequality, not the y equals mx plus b form. Now, what does our final answer here mean? Our final answer means that any ordered pair in this shaded region is a solution for this inequality. You can plug any ordered pair in this region in for x and y, and you'll get a true statement. A dotted line means that points on the line are not solutions. So any point on the line, if you plugged it in to this inequality, you would get a false statement. We can see that statement right here. A dashed line indicates that points on the line are not solutions, and a solid line indicates that points on the line are solutions.